Uh, Welcome to our ongoing series of gibbscam instructional webinars. In this session, we're going to cover the introduction to rotary milling. Rotary milling in gibbscam can be performed with the fourth axis turning simultaneously and the tool moving along the other two axes, or three axes really. The method for creating a rotary milling operation requires that you have the rotary milling module. I'm going to start from the very beginning and show you how to set up a part for rotary milling. In rotary milling, we use this wrap geometry tile to take flat geometry and wrap it around a cylindrical shape on the radius. Now, when doing rotary milling, it's necessary to select the correct type of machine. I've started a file and I've called it rotary mill webinar.bnc. The stock definition is based on a rectangular piece of stock. Now the machine selection is a 4-axis vertical mill that is accessed from your drop-down menu in the machine section of the document control dialog. Material selection, as always, and this is common across the board in all modules, is done from this drop down here. I'm going to machine 6061 T6 aluminum. To do so, I need to select the correct family. Aluminum alloys in the rot condition sets up the conditions for the correct aluminum alloy grouping. The group in this case is none, but the hardness is selected as 75 to 150, the upper temper and the aluminum alloys. If I scroll down in this window, I notice that 6061 is part of my selection set. So if I use the material database in gibbscam, it'll give me feeds and speeds consistent with this selection set. My input method will be in inch units. Global settings for solids does not apply when machining geometry, so I leave this unchecked. The stock is defined as a rectangular shape as it extends from the fourth axis. The rotary axis setup is performed by clicking once on this tile. This tile brings up the fourth axis setup, which allows us to select the axis direction that the fourth axis will be positioned on the machine tool. X, positive, places the rotary axis on the left hand side of the operator as he stands in front of the machine. Unchecking positive puts it in the X negative orientation, which is more familiar to most of us, I would think. When you walk up to a machine, you find that the rotary axis is typically on the right hand side. We can place it along the y-axis, positive or negative. And in certain situations, we can even use the z-axis where we're rotating around z with the turntable. Placing it upside down is a little bit inconsistent with what we can do on a machine, but the choice is there. I'm going to select X minus, placing my fourth axis on the right-hand side of the operator as he approaches the machine. The Y and the Z input boxes determine the center of rotation for this particular rotary axis. Y0, Z0 establishes the center of rotation at the center of the rotary axis. When setting up the tools on the machine, the Z offsets have to reflect the distance from Z0 to the center of rotation. All of the depth values are positive from the center line up. Placing numbers in these values, for example, the Z, would give you eccentric rotation and may not be consistent with what you are trying to do. So my recommendation is to set these values at 0 and make the adjustment at the machine where you can touch off the top of the part and then dial down the center line and use that in your offsets on the machine. Some shops have predefined standards at that height. They come in and they touch the standard with all their tools to set the values there. Other times you can actually touch the top of the fourth axis, or if you've got a tool setter, you can establish the distance that way. So it's important to understand that the tool Z offset is the center of rotation on your part. The axis limited checkbox allows us to limit the rotation as a min and a max limit value. This can be used when your part is longer than the distance from the center line to the table, and you're going to encounter some interference if you do a full rotation. You could limit the rotation. I'm going to go ahead and close this fourth axis dialog up. We've set it correctly. We set the conditions correctly. The stock definition is based on how the part will lay on the machine. I'm just starting with an X value of 6 inches, making my X 0 on the left side of the part. X minus 0.1, give myself a little margin in case I want to machine off the face of the part. The Y value determines the radius of the part that's going to be cut. In this exercise, I am going to be machining a 3-inch diameter cylindrical piece of stock. In order to define it properly, you define it 1.5 in the Y positive direction, minus 1.5 in the Y negative direction, and the Z inputs reflect the same values, 1.5 positive, minus 1.5. This again establishes the center of the part as the center of rotation. The clearance plane, I typically make my clearance planes 1 inch above the part, so my clearance plane will be Z 2.5. 2.5. Tool holder class, I'm going to select a CAD 40. Is pretty common in most machine shops. And the comment, for the sake of having a comment, will be Rotary Demo. All right, once we've satisfied all of the inputs, we're happy with the result. We'll close the dialog, and I'm going to unzoom isometric view, turn on rendering, and see that the stock is defined as a rectangle. We knew that was going to be the result based on the stock definition here. As I mentioned, I'm going to be machining a 3-inch diameter round piece of material. So what I'm going to do is I'm going to establish a stock work group. Stock work groups can be used to create a shape to machine from. Typical of solids, when you can select a solid body for a rendered image, you can do it with geometry in the regular modules. What we're going to do is open the workgroup list, take the first workgroup, and I've already pre-named it stock, knowing ahead of time that this will contain my stock definition. To create a stock workgroup, you name it, you right mouse click the workgroup, and in the drop-down menu, you'll see that there are a series of choices: workgroup info, new workgroup, delete the existing workgroup, duplicate visible workgroups, duplicate and apply any of these functions. And I'm sure these functions look familiar to you because they are located in the modify menu. The same set of functionality is available right here. We've got the sort function for drilling, reverse arcs, change CS, and as I mentioned, all this is available in the modify menu. The choice that I want to make is WG info. Right mouse click it, I'm sorry, left mouse click it. It's a right mouse click on the work group and a regular click on workgroup info. Notice that the workgroup info dialog has two radio buttons that activate different functions. In part geometry, I can check rotary milling, and I'll explain that in more detail in a moment. Part stock allows me to define my geometry as either a revolved shape or an extruded shape along a given axis. In this case, I am going to define a 3-inch diameter piece of stock. To do so, all I have to do is create a circle at the origin of my work group. I'm going to open my geometry creation palette, open the circle creation tile, circle with a center point and a radius, and in the absence of a center point, because typically I would pick a center point and create a circle based on the radius, and I don't have one, so I'm going to click on the CP tile. The CP tile stands for center point. CP X0, Y0, Z0, radius equal to the radius of my defined stock, found right here. Click on the single feature tile. It creates a circle at the origin. If I was to turn on rendering, the rendered image would now reflect a circle. Consequently, any shape can be used here. Just to illustrate, I'll dump that circle. I'll create a predefined shape. I'll select polygon. This is 6 sides. This is to a corner. 1.5. Center position X0, Y0, Z0. Do it. Close my polygon window. Turn on rendering. And the result of that starting stock is now a hexagon. So as you can see, generating stock work groups is fairly easy. That's a revolved stock work group. If, just to take it a step further, if I wanted a revolved work group, I would create a shape, a cross section of a part, for example, with the mouse line. And I'm just going to do a simple shape here. Do a cross section of a wall thickness, like so. Revolve it. We'll be revolving around the x-axis. Turn on rendering, and you can see the shape reflected here with a hole through the center. Okay, dump this, and we'll go back to the original circle that we are going to base our stock on. And turn on rendering. Whoops. The result is a revolved shape, which gave me a sphere. I actually want to extrude that in the x-axis. There we are. That's what we're going to start with. All right. Once we've defined a workgroup as stock, we leave it alone. The rule is one stock workgroup per file. In this case, we've defined it. We've drawn geometry in it. Now we just forget about it. Our actual geometry to be machined is going to be built in an adjoining workgroup. So I'm going to build a new workgroup, and I'm going to name it geometry. I'll right mouse click the geometry workgroup, click on workgroup info, and since I'm going to define geometry that is going to be wrapped around a cylindrical shape, I'm going to turn on rotary milling, and by turning on rotary milling, it activates the wrap geometry tile right up here in the taskbar. When I use this tile, I can actually wrap the geometry around the cylindrical shape or flatten it out. If this tile is not checked, this checkbox is not checked, this tile will not do anything for you. So we're creating part geometry in rotary milling mode. If your installation does not show rotary milling, you may not have rotary milling on your licensing scheme. Okay, we'll close this up and close this window up. Now, my intention is to create a pocket on the OD of the part. To do so, I'm going to create some geometry, open my geometry creation palette. I'm going to go with an easy shape. Make it let's go with a box to keep it simple for now. This box is going to be 3 inches long in X and 1.5 wide in Y. The center position will be X 3 inches, the center of my part, Y 0, and Z 1.5. The radius of the part is defined in Z because I want to lay the geometry on the OD of the part. I'll say do it, close my rectangle dialog, close the geometry creation dialog, and I'll see that there is a fully connected shape at the top of my part. Now, I mentioned that by checking off the rotary milling checkbox in the workgroups, you're able to wrap the geometry. And this is illustrated by clicking on this Wrap Geometry tile. You can see that the geometry wraps around that 3-inch diameter. Now, placement of the geometry is critical to the amount of material that you're going to remove in this pocket. If I was to move this geometry up or down, the radius of the wrap would change based on the radius of the part or the radius of the height. For example, if I double click this shape, modify, translate, and I'm going to translate it down. I'm going to translate it down in Z minus 0.5. Do it. Wrap it. You'll see that the wrap is a lot tighter. If I go down another 0.5, let me unwrap it. Unwrap it. See how tighter the radius gets. So based on the radius, we determine how much to wrap the geometry. Take it back up, 0.5, wrap it, you can see it. Take it up another 0.5, back up to the top where it was, rewrap it, and you see it wrapping on the 3-inch diameter. Geometry can be translated, as you saw, in XYZ. If I turn on wrap geometry, the translation values change from XYZ to XAR, X being the x-axis, A being the angle, and R being the radius. For example, if I want to translate that geometry 90 degrees on the angle, I'll type in 90 in the letter A, do it, and it rotates 90 degrees. If I unwrap it, it unwraps in the flat state up above the part. Rewrap it, rotate it back minus 90, and it goes back to the origination. So the wrap geometry tile activates the XAR value, letting you translate wrapped geometry. All right, we got a simple shape here. Let's do some machining. Tool list, cam list. I'm going to create a tool. Simple tool. Finish end mill, 4 inches long, 0.5 diameter, 0.03 corner radius, 3 flutes, 1.75 length of cut. I'm going to use a tool holder, extended out of the tool holder 2 inches. Tool length offset number 1, cutter comp offset number 1. I want my cutter comp offsets to reflect the tool length offsets, so I set up the sequence of my first 2 tools, and from then on, it'll toggle in the correct sequence. Spindle direction forward, and I have a mill holder, and I can change the holder by using the scroll bar and picking a holder that's more consistent with what I may have in the shop. I'm going to go with this one here. My tool material, I'm going to go with a tin-coated, titanium nitride-coated high-speed steel end mill. I'll put pocket in the comment, close the dialog, and we'll bring down the tool and the pocketing or rough operation on top of it. I'm sure we're all familiar with the dialogues or the text inputs, so I won't dwell too much on them. I'll just kind of go through them and fill them in. First of all, I'm going to select an offset pocket. Speeds and feeds can be taken right from the system. If I don't want to use these values, I can click on the material dialog, come down to the lower right corner and suggest a different value. Maybe I want 800 surface feet per minute with a chip load of 2.5 thousandths. Calculate RPMs, calculate feed, close the dialog, and I've adjusted my feeds and speeds. If I don't like these, I can do a user input. Maybe I'll go 3,500. Entry feed of 10 and a contour feed of 20. My cut width is defaulted to 0.22. 0.22 is the length of the flat at the bottom of the end mill. Remember, we defined it with a 30 thousandths radius, so half the end mill is 250 minus the 30 thousandths radius. The cut width equals 220 thousandths. I prefer to use cutter radius compensation, so I introduce cutter comp with an entry line and an entry radius. I'm going to go with a 30 thousandths entry line and a 0.125 entry arc. I can use a perpendicular line, or I can get into the advanced entry exit moves here. But to keep it simple, and we'll go with a line and a radius. Pocket stock and island stock is material to be left on either the inside of the pocket or the outside of an island in a pocketing or roughing operation. Z-stock will leave material on the floor for a subsequent cleanup. Overlap bypasses the start point at the end of the cut by the specified amount. Spring passes is a deflection pass at each depth. Use stock applies a different algorithm when cutting outside of the stock. I'm going to go ahead and uncheck it. Now, to set my depth values correctly, I like to interrogate the features that are on screen. For example, I want to determine the top of the cut right here. So to interrogate it, I highlight the dialog, hold the Alt key. It turns the cursor into a square interrogator. I click on a point on the geometry and it fills in the dialog for me. So this geometry is at 1.5 in the Z-axis. This lets me adjust my rapid approach to 1.6 and my rapid retract to 1.6. This ensures that I won't crash into the part on approach. Now my depth of cut, I want to cut 200 thousandths deep. As I previously mentioned, all depth values are positive from center line. See this black line here? This tells us that all the values are up from this line. If I want to cut 200 thousandths deep, I let the system do the math for me. I establish the top of the cut at 1.5, and I subtract 0.2. That makes the full depth of cut at 1.3. My desired step is 200. I'll use retracts, depth first, prefer subs, auto plunge, and round corners is on. It should always be on when machining. Even if you're not breaking the corners, just use a 0 corner break. You'll get a better tool path using round corners. You'll roll around a corner instead of bypassing it and changing a direction with round corners on. CRC stands for cutter radius compensation. We want to activate that. Climb cut. I always like the climb cut. Better results, better finish, longer tool life. And flood coolant is going to be used. Close the dialog window. Pick the geometry. And it's not necessary to pick the entire shape. If you just pick one section of it, the fact that it's fully connected identifies the entire shape. I'll say do it. And there's my tool path. If I render it, we're going to see the tool path start in the center and give us a nice flat cut. Now, if I was doing wrench flats, this would be ideal. I'd put one up here, duplicate it and rotate it 180 degrees at the bottom, and I'd have wrench flats. But that's not the intent. The intent is to create this pocket in rotary mode. If I wrap the geometry, we'll see the effect that I'm looking for. Now, simply wrapping the geometry will not cut this in rotary mode. As you can see when I hit the redo, it still gives me a flat cut, even though the geometry is wrapped. To get a rotary tool path, you must highlight the process, go to the Rotate tab, and select Rotary Milling. Rotary Milling in the XY plane, close the dialog, redo the operation now, and you see the tool path is now following the contour. If we're to render it, we see that moving, and we'll even try, let's try some simulation here and see what we get. Here's simulation. We could go into tool mode, and we could actually step backwards in the simulation with the coarse control and the fine control. There's regular simulation there, and whoops. Go to Machine Sim here, which is the mode I was looking for, which will actually show the part moving instead of just the tool. All right. So that's how we get a rotary pocket on the OD of a part. Now let's make a couple more operations. What I like to do is create a series of holes. We'll make a hole by specifying a point and then doing a duplicate and rotate around the cylindrical shape. So what I'm going to do is I'm going to deselect the operation, click off screen, throw away the process, which is usually done every time we want to create a new operation, and I'm going to build a new tool. The new tool will be a drill. It'll be a 1/2-inch drill, 4 inches long, 118-degree angle, default angle, and the drill will have 2 flutes. In order to drill, we need a point on screen. So open the geometry creation palette, select the point tile, XYZ, X1, and notice that my dialog says XAR. The reason it says XAR is because I'm in rotary mode. If I uncheck wrap geometry, it goes back to linear mode, X, Y, and Z. So I want to hold at X 1 inch, Y0, Z 1.5, and it puts a point right where I want the hole to be drilled. Close the geometry creation palette and bring the tool down, the drilling process. We're going to do a peck with a full out. Notice that the system has retained the information for the rapid approach and retract at 1.6. Stock is at 1.5. And I'm going to take the shoulder of the drill all the way to 0. So we get some intersecting holes here. Speeds and feeds look okay. I'll close the dialog. Now, I forgot to click on the rotate tab. Go back to the rotate tab, and we're going to do this as a position starting at angle 0, which is the top of the part. I'm going to duplicate it 7 times at 360 divided by 8, which should give me 45 degrees. Pick the point and do it. If we render it, we'll see the pocket, and then the holes are drilled all the way through. As you can see, the rendering looks a bit rough. We can tighten that up and smooth it a little bit by going to the render control and settings. Change the cut part chord height to 0.001. 001, apply it, and let's see if we get a better result here. Much better. Notice that the holes are now round instead of octagon, and this is accessed with the right mouse click, settings, cut part chord height, and chord height are visual settings for the rendering. We can speed up the rendering by increasing the steps per update. If I go to 20 here and apply it, I'll get much more speed out of my rendering. As you can see, the rendering is much quicker. So you've got control over how fast we render the part, just knowing where to find the settings. If you have any issues, you can always send an email to support@gibbscam.com. We'll be glad to answer your questions and direct you to where these settings are. All right, let's close this up. That was fairly easy. Go back here, rotate, tell it how many times you want it. Say we don't want to duplicate it, but we've got a point at 0, 0 up at the top, and I want to actually machine it on the other side, so I type in a -90. The point is selected, I redo the operation, and the machining is performed at 90 degrees. A little too fast. I may have sped it up too much. There's our pocket, and there's the hole at 90 degrees to where the point was actually drawn. Easy enough to put it somewhere else. All we got to do is change the angle. Say 235 degrees. Redo it. Render it. Get our pocket going. And the drilled hole at 230 degrees. Okay, so pocketing, drilling, pretty straightforward. When you're in rotary mode, it's a matter of just selecting the geometry, getting the correct values for the top of the part, the depth of cut, and treating it like you would on a normal flat situation. Let's get a little bit more involved here. Let's create a thread. We're going to use a contour pass to generate a thread along the length of the part. I'm going to make a new work group. New work group. We'll call it thread. And this is going to be in rotary mode also. So I'll right mouse click the work group, go to WG Info, select Rotary Milling, close the dialog, and deselect the operation, throw away the process, and draw some geometry for a thread. Now, to generate a scroll or a thread across a cylindrical shape, we need to know some information. First of all, we need to know how many threads per inch, or the pitch of the thread. Let's cut an 8-pitch thread along the length of this 6-inch long part. So that's 8 threads per inch. Okay. The first thing we do is we establish a point at the beginning of the thread and a point at the end of the thread. The first point is placed in linear mode. The second point is placed or located in rotary mode, and I'll show you how to do that in a second. First off, we bring up the geometry creation palette. I'm going to turn off the tool list and the cam list for now. A little bit less clutter on screen. As I mentioned, we create 2 points. The first point, X, Y, Z, is created in linear mode, X, Y, and Z. X 0, Y 0, Z 1.5. Multiple feature creation tile. Creates the first point right at the beginning of the thread. The second point, as I mentioned, is created in rotary mode. Click on Wrap Geometry. Notice that XAR are now the axis letters. X6, the end of the part. Now the angle is where we have to do some calculations or some math. We know that the part is 6 inches long as defined in the document control dialog right here. We are generating an 8-pitch thread, which is 8 threads per inch. So what we do is we multiply 8 times 6. So it's 8 times 6 equals 48. So we've got 48 threads along the length of this part. Now those 48 threads are multiplied by 360 degrees because each thread does a full revolution. 48 multiplied by 360 degrees, and the radius remains at 1.5. I'll click on the single feature creation tile. The point appears at the end of the part, and it looks no different from the first point that we placed in linear mode. So the next step is to connect a line from one point to the other. We do this in Wrapped Geometry. We select the line creation tile. You pick the two yellow points. Single feature creation. Look at the line. If I unwrap it, it goes straight. If I wrap it, it wraps around the radius. The next step is to terminate the line at each point location. Here, connect, select the arc, control click the other point, connect, and watch the result. Look at that. There is our thread in wrap mode. If I unwrap it, it is a straight line, which is 17, I forget what it was. Let's see. Oops. 280 inches long. All right. Easy enough. Now, let's go ahead and machine this. Tool list, cam list, new tool. I'm going to machine it with a spot drill that's on a 60-degree angle to give me a 60-degree V. Everything else remains the same. Close the dialog. I'll bring this down, and as I mentioned, this is going to be a contour cut. Feed the speeds look good to me. Entry exit moves. I really don't need a radius, but I do need an entry line for compensation. Stock values are 0, overlap, spring passes are 0. My approach is still good. My top of cut is still good. My depth of cut is going to change. I only want to cut this maybe 60 thousandths deep. So once again, establish the top of the cut, subtract the depth of cut, and my desired is 60 thousandths deep. Okay. Rotate tab. This is machined in Rotary Milling. Close the dialog window. Pick the start point. Pick the center circle to cut on center. Start point, end point. And let's move my start point. Move start end point by 0.2. Apply it. And it moves it out off the stock. That way I'm starting off the thread. My end point, I'll move that by 0.2 also. And it pushes it off the geometry by 200 thousandths. All right, we'll take this information, tell it to do it. Toolpath is created. And I actually want this to be my first operation. So right mouse click the operation, move to, number 1, move to, goes right there. Close the move op dialog, render it, and speed it up a bit. We'll see the thread cut. There's the pocket and the hole. So our part is starting to come together here. I look at it and I see that actually I can start further out and clear the part And what we're going to see is that we can extend this cut further out. Turn off rendering, take this, drag this tile out here for the sake of, whoops, where'd we go? Let's go by 0.5. Move it further out, redo it, and now let's look at it, see if we get a better start. It looks like we'd have to create another thread here, but we're okay. Now, we're not limited to straight threads. We can create a tapered thread if we like, and that is done very easily by changing the height of the last point. If I recreate this geometry to make a tapered thread, I can show you how to do it here. Double click on, let me close this up. Double click. I'm going to keep this point, throw this away, make a point XYZ in rotary mode. Same values, except the radius is set at 1.5, 1.25. Put the line between the points. We get a tapered thread, and easy enough to machine. Double click on that. Everything updates, redo it, and let's see what the result is. If I redefine my stock to reflect the taper, this would render correctly. But for demonstration purposes, you see that we are getting deeper as we progress along the thread. There we go. All right, so threading, pocketing, drilling holes, pretty straightforward. Keep in mind that the tool always points to the center of rotation in the rotary milling module. Let's create one more piece of geometry. Let me show you how to do some engraving. I'm sure that we're all familiar with the gibbscam splash screen, the application screen that shows the rotary mill part with gibbscam on it. Let me show you how that was done. I'll just briefly go over how to create some engraving and put it on the cylinder and machine it. So what I'm going to do is build a new work group, and I'm going to call this letters. Okay, right mouse click, work group info, rotary milling. All right, pretty straightforward. Shapes, engraving. Engraving takes a moment to load the font directory. My alignment point will be X3, the center of the part, Y0, Z, 1.5. The font, without getting too creative, we'll just find something Arial bold italic looks good. The grid in the center, and my letter height 0.75. Central alignment, my spacing 0, 0, uses the parametric spacing of the font to space the letters. My text flow is from left to right in a straight line. Additional rows created downwards. And my text will be something familiar. do it, and there's my text. It's in wrap mode, you can see. Now, that's straight along the cylinder. What I'd like to do is put it at an angle. So hold the Shift key, drag a window around the entire lettering. It'll all select, modify, 2D rotate around X3, Y0. In the counterclockwise direction, give me, let's try 30 degrees. See what that looks like. Wrap it. That looks good. Let's try a little more. Maybe 40 degrees. That's a little bit more radical. Okay. So there's our text. Unwrapped, wrapped. Close the dialog. Open the tool list, the cam list, and I'm going to do the engraving with a very small ball end mill. Let's go with the let's see, we'll go with the 1/32 ball end mill. Overall length, maybe 1.75. 2 flutes, 0.5, and length out of the holder, 0.625. There we go, nice and small. Unwrap the geometry, bring the tool down, and we'll do it as a contour the first time around. Then we'll pocket it out. So contour cut, leave the same values, 0 entry moves. I'm only going to go 30 thousandths deep, or maybe 15. So 1.5 minus 0.015. Okay. Rotate tab. Rotary milling is selected. Control A, select all. Do it. And as you can see, the toolpath appears first flat and then it wraps around the cylinder. I'm going to move this to my first operation. Move to number 1 and render it. Let's see what we got here. I don't want to wipe it out, so what I'm going to do is I'm going to skip unselected ops and show only the first one, because that is the only operation selected. As you can see, the contouring is performed. What I'm going to do is, just for kicks, I'm going to change holders. That one's a little bit big. Come over to my holders. And I like this holder better. Let's look at it again. Rewind it and change the holder. Much better. Much better. All right. Now that's a contour pass. It goes around the letters. If we wanted to do a pocketing operation, bring down the rough tile. Offset pocket. Everything looks good. Cut width, maybe 0.005. Get it nice and fine down there. Redo it. And there is our... Now you notice that the letters may be out of order. You can't correct that by copying and pasting or cutting, taking the letters and cutting them onto the clipboard and re-pasting them. It'll resequence the operation. Or if you wanted to, you could physically come over and adjust the order by dragging the tiles to the location that you wanted them at. There it is in pocketing with the letters cut out of the cylinder. Now, we can go the other way and leave the letters raised instead of pocketed out. To do so, I'm going to trim this off. To do a raised letter situation, we'd build a piece of geometry around it, create like a pocket operation. I'm going to create a simple shape using mouse line. Look at it from the top view, and I'm going to take and just draw a containment boundary around my geometry. Double click my operation. That's selected. Pick the boundary. Redo it. Whoops. Let's do this. Pick the boundary. Should have picked all the letters. Top view. And let's do it this way. Rotate this around so I can get my shift window over the text and redo. Here's the problem. I found the problem, guys. I apologize. This geometry needs to be at 1.5. Force depth, 1.5. Do it. Problem solved. My geometry was lower than. There we go. My geometry was lower than the letters, and therefore it was cutting the letters as pockets. Now we can show it. With the pocketing routine, taking out all the material and leaving the letters raised. It'll take a moment because we've got a very fine step over, and I've got the rendering turned up all the way. While this is happening, you notice that there's a series of empty spaces along the completed operation tile list. If I hold the shift key and double click an empty tile, it pulls up the operations that are down below. It also restarted my rendering because of the fact that I was picking unselected ops. I was clicking on empty tiles and there's no ops selected. If you have any questions, concerns, or comments, don't hesitate to email support at gibbscam.com. If some of these features require more explanation on your part, please let us know. We'll be glad to help you through this. If you have files that you're working with using Rotary Mill and you encounter problems, you're always encouraged to send them to support@gibbscam.com, where we'll take a look at them and get back to you with a solution pretty quick. Now, just keep in mind that we attend to files in the order of reception. Sometimes you may get a quicker response than others. It all depends on the workload here at tech support. We will be holding more sessions as time goes on. We'll cover the basics, and then we'll actually gauge demand and structure some sessions for the MTM, 5-axis, and advanced milling, advanced 3D milling functions of gibbscam. Granted, this program would take a long time, and you see it's already into 45 minutes, 46 minutes, but based on the step over, feeds and speeds, the time can be optimized. gibbscam also has a more enhanced version for rotary machining, which is called the 4-axis module. This module allows you to move the cutter off center and Y and do quite a bit more with the rotary mill option. So you have options as to which module you can purchase or use based on your needs and the type of work you do. Here's our gibbscam logo wrapped around a cylindrical shape. If we wanted to see the rest of the operations, of course, it's just a matter of highlighting them and doing them. We'll reset that. Instead of having these 4 highlighted, we'll highlight these ops right here, and we'll show the skips the unselected op and the entry plane. A nice red mark. That's because the entry plane wasn't set correctly from the previous op. I'm skipping operations. All right, gentlemen. Thank you very much for attending. And as I mentioned, we will be holding more. You will be receiving invitations in the near future. Any concerns or issues, please contact support@gibbscam.com. Thank you.